everybody.
Paul with the U of I Physics Department is joining us now. Good morning.
Good morning. How are you guys?
Thanks for being here.
And first off, we want to start out with a birthday shout out to someone special, right?
Yeah, my dog Bumper is 6 today.
Oh,
I'm
happy
well.
birthday, Bumper. That's why you got the get up.
That's why I got the boat.
Well,
signed.
Paul also likes it. You like this get up too.
I love it. It's awesome.
It is.
Cool.
So what are we learning about today?
Today is all about ultraviolet radiation. It's kind of a little continuation. So we talked about radiation last time I was here, and we had the spectrum up that you guys can show again. So,
Bring that up in just a second here.
Spectrum of electromagnetic radiation. So we have light. So light comes in the form of photons, and the ones that have longer wavelength, those are the red ones, those have less energy, and the ones that have shorter wavelength, those like blue, those have more energy.
Okay.
And most things, I have a little light tree here that has a bunch of different colors coming out, going from red at the top all the way down to blue at the bottom. Okay. So normally when you shine light onto an atom, you excite the electron, you pull it a little bit away from the nucleus. It's kind of bound to that, but it pulls away, and then a billionth of a second later, it drops back down and it gives off that color. So that's how we see most things.
Right.
And we said last time that, well, if you have something that's like ultraviolet, it's possible that it can excite it up, and then it can kind of vibrate down a little bit, and then it emits something. So it can be excited with ultraviolet, but can emit in the blue or something like that. And that's what we have, or in the green. So I have here some ultraviolet lights, and if I just shine on this fluorescent sheet, hopefully you can see that it's nice and bright. So it's emitting in the green, even though this is ultraviolet.
Sure. Cool.
Okay, but there is another thing that ultraviolet light can do, which is that it has enough energy that it can actually rip off the electron altogether or break a chemical bond, and that can be bad for us because that could, for example, damage DNA, and that can cause cancer, basically.
Yeah.
That's how cancer can start. And it can also change the shape of materials. So if you break a chemical bond, things can bond together in a different way. So for example, I can have some carbon atoms that normally are bonded perpendicular to each other, and then if an ultraviolet photon comes in, they change. And when they change, it's a longer molecule, so it can absorb longer wavelengths. It can absorb visible light. So something that normally can't absorb visible light, if it absorbs ultraviolet, can suddenly absorb visible. And I have an example of that, which is sitting right here. So this is just a panel of beads, of these ultraviolet beads. And if I shine on ultraviolet light onto them, what you will see happen is that they will all change.
That is cool.
That is really cool.
Yeah, so they're actually a different color now than they were before.
They are. Oh my gosh.
And
awesome.
That's fascinating.
So why is that? Why might that be useful? Because you can make necklaces and things like that. And sometimes you might have seen like T-shirts that have things like this.
Yes, I have. Yeah, and nail polish even now too. They have that.
Yeah, exactly right. So there's maybe a more common example, which is they can put this sort of a photochromic material onto glasses. So these are things that will turn gray or turn darker when they're in sunlight. So right now they're transparent, so they're passing all the visible. But turns out that they absorb ultraviolet. And so if I just shine some ultraviolet light onto this right there, you can see what happens.
Oh my God.
The transition.
Yeah, it goes completely dark. And I'm going to do that on both sides. And just so
Gotta have a pair of eyes,
do
right?
a comparison. Yeah, exactly. Now we have a pair of eyes.
That is so very cool.
Great.
Okay. I love that.
So the other thing that, just kind of an aside, so when these relax, so right now the molecule's in this other shape, and then it thermally relaxes back to its original state as a thermal
And that's
process.
how it gets back to
from
the
vibration.
clear.
That's how it gets back to the clear. Now the question is that more likely to happen if it's in a hot or a cold environment, if it's a thermal process?
I'm sure you're going to tell us.
I'm sure you're gonna make a prediction.
Oh, I'm not sure.
What do you think?
Cold or hot if it's a thermal process?
To go back?
To go back.
Cold.
Yeah.
Cold will be faster? Or
No.
See, now I feel like...
Which is slower, which is faster?
Wait, hold on a second.
Faster to go back?
Yeah.
Cold is faster, isn't it?
No.
Warm is faster.
Warm is faster.
Warm, well, let's see.
He's making me question everything.
So I got a hot cup of water here. This has just been tea I've been making. And we're just going to let it sit in there for just a second. And on the other hand, I got a cold one. I'm just going to, well, I could dip it in, but that's not going to show us very much because it's really cold. But basically what we'll see is that the hot one, if I put this again on the hot one is the one that was this one. Right, and it's much more recovered. So if you ever come in like in the winter, you might find that your glasses are really dark for a long time. If you've run them under hot water, then they will reset much more quickly if you wanted to do that.
All right.
Very cool.
Okay, but so we know that ultraviolet can change colors and things like that. So what we need, ultraviolet can also damage things. So we need to protect ourselves. We need to protect our eyes, and we need to protect our skin from that. So we can protect our eyes using sunglasses. So normally, just normal sunglasses, most of them will now block ultraviolet light. And so if I go back to my my little surface here, and I shine this on, let's see if we can. I don't know if I can get the thing to show that in the shadow, there's a shadow
you
of
can
it. And basically, yeah, there we go. It's blocking in the shadow. So old style glasses didn't always block UV, but I tried yesterday to find a bad pair of sunglasses, and I couldn't find any
so
bad
that's a
pair
good
at
thing.
any
That's
store.
good to know.
Yeah, they all block
That's comforting.
UVA, UVB. Okay, so in fact, there are different types of UV, if we put up the chart for that. So the worst of them is the very short wavelengths, UVC, and those completely can break apart things because there's so much energy, but that's almost all, basically all blocked by the ozone in the upper atmosphere, so we don't have to worry about that. And then there's UVB. That's like from 280 to 320 nanometers. So you can't see that, but that is what causes sunburn. It also what causes a suntan. So you promote melanin, and that darkens your skin, and then that protects the rest of your body because then the sunlight doesn't get in. It can also cause cataracts. But not to say that all UVB is bad, so we need it because we need it to synthesize vitamin D, and that actually makes serotonin, which makes us happy. And then finally at the other end, and UVB is partly blocked by the atmosphere, and then finally we have UVA, which is longer wavelength still. It's not nearly as dangerous, although it can promote aging of skin and can still be damaging. And but some of that does get through the atmosphere. So if you're going to get like a suntan lotion, which is what the last thing we're going to talk about is suntan lotion, you want something that can block both the UVA and the UVB because both of them are damaging, and there's a lot more UVA around than there is UVB. So you want a so-called broad spectrum.
Yes.
And
Well, you've got a bunch of them here.
I do have a bunch of them, and they're in order of the SPF number. So this is actually just lotion, which doesn't do anything, and this is like SPF 50.
And real quick,
15.
before we wrap up,
Yep.
what is the importance of the grade of it and how?
Right, so if we do the last little chart here, which the SPF is a sun protection factor, it basically tells how much of the UVB is protected. And so if you have something like SPF 15, that means that only one of every 15 photons gets through, and SPF 50 would be only one of every 50 photons get through. So if, for example, you have something that's SPF 15, it means that you could stay out, in principle, 15 times longer than you normally would. So if it normally would take you an hour to get a sunburn, then you could stay out for 15 hours. And with SPF 50, you could stay out for 50 hours, except that's not true at all because it washes off and it sweats off after only a couple hours. So you need to reapply very often. And the last thing, which I can show with the demo, again, is I've made a sheet here that has a bunch that's actually taped up on, it's actually held up on the front here, that has a bunch of these on, in order from lotion to SPF 15 to 30 to 30 to 50 to 70 to 70, and then a mystery thing over there. And so I'm just going to shine my ultraviolet light, and we're just going to look at the shadow at the back, and we can see that it gets through like these lower SPFs pretty well, and then there's more and more of a shadow as I go to the higher SPFs.
Right.
And then at the very end, I have this one, which is really dark. And the question is, what's that? And that is SPF 30, but it's SPF 30 that's in a thicker coverage. So the thing is, if you put on a thick layer of SPF 30, it's going to be just as good or even better than a thin layer of SPF 50. I guess the worst thing or the message there is that if you put on SPF 70, but you put on way too thin of a layer, it can be just like SPF 5 or something like that.
Very enlightening. Thank you,
So,
Paul. That's awesome.
Stay healthy this summer.
Stay safe and healthy. Thanks,
Lather up.
Paul. We'll be right back with more in the morning show, you guys.
Thanks, guys.